Nenomatica, where mathematics meets YouTube excellence. In this lesson, we will master how to simplify powers sitting under a radical by adjusting the index. We will prove the rule, discuss when absolute value is required, and finish with two clear examples. Theorem: for non-negative a and any natural number k, the nth root of it equals the k nth root of a to the k. This is the engine that lets us move the exponent out of the radicand into the index. Proof idea using exponent rules. The nth root of it equals a to the 1 over n. Rewrite 1 over n as k over kn. That equals a to the power k over kn. Group as a to the k, all raised to 1 over kn. That is the k nth root of a to the k, QED. Important note, for real a after raising to the k, and then taking a root, parity of k matters. If k is odd, no sign change occurs, and the result behaves like the nth root of a. If k is even, the sign inside becomes non-negative, and we must use absolute value. Here is the precise statement. We'll use two quick examples to make the rule crystal clear. First, the two key rules. Rule 1. For an even index n, the principal nth root is non-negative. So the fourth root of a square becomes the square root of the absolute value. Rule 2. For an odd index, the sign is preserved. The cube root of a negative number is negative. Let's apply the rules with two quick worked examples. Example 1. Evaluate the fourth root of open parenthesis negative 9 close parenthesis squared. Because the index is even, use the even root rule. Fourth root of a square equals square root of the absolute value. That becomes square root of absolute value of negative 9, which is square root of 9, and equals 3. Visually, squaring removes the sign, and the principal even root returns the non-negative answer. That's why the result is positive 3, not negative 3. Example 2. Compare these two expressions. The sixth root of open parenthesis negative 27 close parenthesis squared, and the cube root of negative 27. For the left, square first to get 729, and the sixth root of 729 is 3. For the right, cube root of negative 27 is negative 3. So they are not equal. 3 is not equal to negative 3. This difference happens because the left has an even root, which must return a non-negative principal value, while the right has an odd root that preserves the negative sign. In this short lesson, we will follow the exact step-by-step algorithm shown in the prompt to simplify two square root expressions. We will not change the order or add extra steps. Example: we will simplify the square root of 1 over 49 by following the displayed steps exactly. First, write the expression. Then split the square root across the fraction. Next, evaluate the square root of 1 and rewrite 49 as 7 squared inside the root. Finally, simplify the square root of 7 squared to get 1 over 7. Great. Now we repeat the process for the second expression, again following the same exact sequence of steps as shown. Example: we will simplify the square root of 10 to the fourth power. Start by writing the expression. Next, rewrite 10 to the fourth as the square of 10 squared under the radical. Then, the square root of a square cancels to 10 squared. Finally, evaluate 10 squared to get 100. Start with the square root of b to the fourth. Rewrite the inside as the square of b squared. The square root of a square cancels, so the result is b squared. Now, the main problem. Begin with the square root of a to the fourth times b to the 12th. Factor the inside as a single square, namely a squared b to the 6th, all squared. Drop the square root and the square, leaving a squared b to the 6th. That is our final simplified form. Here is the key idea we will use. The product of two nth roots with the same index equals the nth root of the product. Let's begin with example 1. We will mirror the given steps exactly and explain why each is valid. Start with the expression. Next, apply the product rule to merge the two fourth roots. Multiply inside the radical. 28 times 7 equals 196. Now factor 196 as 14 squared. Finally, the fourth root of 14 squared equals the square root of 14. So the result of the first problem is the square root of 14. Now for example 2. We will again follow the listed steps and correct a small simplification at the end. Begin with the expression. Use the product rule to merge the ninth roots. Multiply inside to get 0.008. Rewrite 0.008 as 0.2 cubed. Finally, the ninth root of 0.2 cubed is 0.2 to the power 1/3, which is the cube root of 0.2. So the second result is the cube root of 0.2, or equivalently 0.2 to the 1/3. Summary. In this lesson, we will simplify three expressions with cube roots, following the exact algorithm from the prompt, step by step, without changing the order. Here are the three targets we will simplify: the cube root of a to the third times b to the sixth, the cube root of b to the sixth over c to the third, and the cube root of -64 over 27. Problem 1. We start with the cube root of a to the third times b to the sixth. Step 1 in the algorithm rewrites the inside as a perfect cube, the quantity ab squared, all cubed. Then, take the cube root of that cube to get ab squared. Problem 2. The cube root of b to the sixth divided by c to the third. The algorithm first separates the cube root of a quotient into a quotient of cube roots. Next, rewrite b to the sixth as the quantity b squared, all cubed. Finally, evaluate the cube roots to get b squared over c. Problem 3. The cube root of -64 over 27. First, separate it into a quotient of cube roots. Then, recognize both numerator and denominator as perfect cubes, -4 cubed and 3 cubed. Finally, take the cube roots to obtain -4 over 3. Example: simplify the square root of 4x squared. We follow the algorithm. First, rewrite the inside as a perfect square, then take the square root. The key idea is the square root of a squared quantity equals the absolute value of the base. Rewrite 4x squared as the square of 2x. Then the square root becomes absolute 2x. If we assume x is non-negative, this is simply 2x. Simplify the cube root of 27. 4 odd roots, the sign is preserved, and the cube root of a perfect cube equals its base. Rewrite 27 as 3 cubed. Take the cube root to get 3. Simplify the cube root of -8. Again, 4 odd roots, the sign passes through. The cube root of -a cubed is -a. Recognize -8 as -2 cubed. Therefore, the cube root is -2. Simplify the cube root of 64. Use the perfect cube idea one more time. 64 is 4 cubed. Hence, the cube root is 4. We start with the square root of 18 cubed. We factor the radicand as 2 times 9 times a squared times a. Next, we split the square root. Square root of 9 times a squared times the square root of 2 times a. Then we rewrite the first root as the square root of the quantity 3a squared. Finally, we take the root of the perfect square to get 3a times the square root of 2a. Next item. We have 2 times the square root of 150. We factor 150 as 25 times 6. We split the root into the square root of 25 times the square root of 6. We simplify the square root of 25 to 5. Finally, multiply the constants to get 10 times the square root of 6. Last item, the square root of 128a to the 5th. We group the factors as the square root of the quantity 2 times 64 times the quantity a to the 4th times a. Then we split the root into the square root of 64 times a to the 4th, multiplied by the square root of 2 times a. Rewrite the first part as the square root of the quantity 8 times a squared, all squared, times the square root of 2a. Take the square root of the perfect square to get 8a squared times the square root of 2a, and write the final form as 8a squared square root of 2a. Then the two expressions we will simplify. Before we start, quick challenge. Can you predict the first move? We will combine radicals that share the same index. Rule: product of radicals with the same index equals a single radical of the product. Now step 1. Combine the 2/6 roots under 1/6 root. Rule: multiply coefficients and add exponents of the same base. Step 2. Multiply inside the radical. Notice the new radicand 8b to the 6th is highlighted. Rule: express the radicand as a power to match the index. Step 3. Rewrite 8b to the 6th as quantity 2b squared all cubed. Rule: radical of a power converts to a rational exponent. Step 4. take the sixth root of quantity 2b squared, all cubed. This equals quantity 2b squared to the power 3 over 6. That is 1/2. We correct a minor error from the reference. The correct simplification is b times square root of 2, assuming b is non-negative. Final result for the first expression is b times the square root of 2. Now, we simplify the second expression, keeping the step structure from the image. Rule: quotient of radicals. Step 5. Write the cube root of a fraction as a quotient of cube roots. Rule: factorization of radicands. Step 6. Factor 24 as 8 times 3, and a to the 7th as a to the 6th times a. Rule: product of radicals equals radical of a product, and vice versa. Step 7. Separate into simpler cube roots. Rule: express perfect cubes. Step 8. Write a to the 6th as quantity a squared cubed, and 8c cubed as quantity 2c cubed. Rule: the cube root of a cube equals the base. Step 9. Simplify the perfect cubes. Rule: combine radicals in a quotient. Step 10. Combine the remaining cube roots into one. In this lesson, we will solve 3 radical problems exactly following a clear step-by-step algorithm. We will convert indices to a common index, combine, and then simplify carefully, highlighting every change. Below is our example, and the first expression we will simplify. Product of radicals with different indices. The product of the ATH root of x and the BTH root of y equals the BTH root of x to the b times y to the a. Now we express both radicals with a common index. Multiply radicals with the same index by multiplying the radicands. Step 2. Multiply constants and combine under 1/6 root. Simplify radicals using fractional exponents. Step 3. Rewrite 128 as 2 to the 7th, pull out a factor of 2 to the 1st, and simplify the remaining 6th root. Quick challenge. Can you predict the first conversion step we will use in the next problem before it appears? Now for the second expression. We will divide radicals with different indices by converting to a common index of 15. Rule: division of radicals with the same index means we divide the radicands. Step 2. Combine into a single 15th root, and then rewrite bases in powers of 2. For the last expression, we divide a 4th root by a square root. We first rewrite the square root as a 4th root to match indices. 4th root to match indices. Rule: divide radicals with the same index by dividing radicands. Step 2. Perform the division under the 4th root and simplify to the simplest radical form. Great work! Let's summarize what we used. First, convert different indices to a common index. Start with the example, label, then the orange problem statement. Prime factorization and properties of radicals. Step 1. Express each factor inside the radical in prime powers. 16 is 2 to the 4th. 18 is 2 times 3 squared, all to the 5th. 24 is 2 cubed times 3, all to the 7th. Power of a power. Step 2. Distribute the exponents. Product of powers with the same base. Step 3. Combine the 2's and the 3's. Combine the 2's and the 3's. Rule: radical of a product. Step 4. Split the 6th root into 2 factors. Rule: simplify radical powers. Step 5. Extract perfect 6th powers. 30 divided by 6 gives 5. For the 3 term, take 12 out and leave 5. Now the 6th root of 3 to the 12 is 3 squared. Keep the 6th root of 3 to the 5. Compute 2 to the 5 and 3 squared to finish. Write 3 to the 5 as 243. Answer: 288 times the 6th root of 243. Now a second example with variables. Show the example label, then the orange statement. Rule: multiply coefficients and use radical properties. Group constants first. Convert the radicals. The square root of b to the 4 is b squared, and the 4th root of b squared is b to the 1/2. That is the square root of b, multiply outside factors. Now combine the b powers and merge the 2 square roots into one. Answer: negative 28a to the 4b to the 4 times the square root of ab. Quick summary. We used prime factorization, product of powers, splitting radicals, and extracting perfect powers to simplify. Practice more problems and explore fractional exponents next. Great job following every step. Practice more problems and explore fractional exponents next. Great job following every step. Example: the expression is the 10th root of open parenthesis -2 close parenthesis to the third times -2 to the fifth times -2 squared plus the cube root of -8. Rule: reminder, product of powers with the same base equals that base raised to the sum of exponents. Combine the 3 powers of -2 inside the 10th root. Now add those exponents. 3 plus 5 plus 2 equals 10. So the exponent becomes 10. Next rule: the nth root of a to the n equals a. The 10th root of -2 to the 10th is 2, because the even power makes it positive, and the cube root of -8 is -2. Finally, compute the result. Second problem. Example: the expression is the 5th root of 32 multiplied by the 4th root of open parenthesis -2 close parenthesis times open parenthesis -8 close parenthesis. Use factorization into powers of 2. 32 equals 2 to the 5th, and -2 times -8 equals 16, which is 2 to the 4th. Rewrite both radicands as powers. Apply the root of a power rule again. The nth root of a to the n equals a. Each radical simplifies to 2. Multiply to finish the problem. Here are the 2 expressions we will simplify. The first is the -8th root of open parenthesis -5 to the 13 times -5 to the 75 close parenthesis. The second is the cube root of -4 times -6 times -3 squared. Part A. We begin inside the radical by using the product of powers with the same base. That rule says a to the m times a to the n equals a to the m plus n. Combine the exponents 13 and 75. Step 2. Add the exponents to get 88. Step 3. To extract an 8th root cleanly, rewrite 88 as 8 times 11. Then note that raising -5 to an even power removes the negative sign inside. So we can treat it as 5 to the 8 times 11 under the 8th root. Step 4. Use the root and power cancellation property. The 8th root of a to the 8k equals a to the k. Apply k. Apply it to get 5 to the 11, and keep the negative sign that was outside from the start. Part B. Now simplify the cube root of -4 times -6 times -3 squared. We will factor each integer into primes and isolate the signs. The root of a product can be handled by working inside the radicand first. Step 6. Multiply the 2 negative ones to get +1, then collect bases. 2 squared times 2 is 2 cubed. 3 times 3 squared is 3 cubed. Step 7. Use the root power cancellation again. The cube root of a cubed is a. So the cube root of 2 cubed times 3 cubed becomes 2 times 3, which equals 6. Our final simplified answers are, for part A, -5 to the 11. For part B, 6. Quick summary. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.